Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle devrimlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler günü umursamazlar. Robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar. Hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar. Asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Hello everyone, welcome to the third session of our conference, and today in this session we have 8 papers, a total number of 8 papers, and 4 of those papers are about modeling in geotechnical engineering, and the other 4 is about emerging subjects in geotechnical engineering. Our first paper is titled Field Trial to Rapidly Classify Soil Using Computer Vision with Electric Resistivity and Soil Strength. And it will be presented by Ujun Al. And please go on, Ujun. We are listening to you.
Yeah, just to check and hear, right? Yeah. So good day, everyone. I'm Eugene. I'm a PhD candidate and research engineer from the National University of Singapore. So today I'm here to share research findings co-authored with my colleagues from NUS and also HDB on this paper Field Trial to Rapidly Classify Soil Using Computer Vision complemented with electrical resistivity and soil strength. So the brief outline today is introduction on the project, the objectives of the research, methodology, research results and discussion, and finally conclusion. So a short introduction. So in Singapore, we are a small country in Southeast Asia. So we have limited land and natural resources. So we reclaim land not by using sand only, but we also recycle excavated soil from construction works all around the island. So this includes tunneling and excavation works. And after the soil are excavated, we transport them using trucks to facilities from what we call staging grounds. And over here, the soils will be loaded onto barges where they will be transported to the reclamation sites, and they are used for various reclamation works that depends on the soil property and quality. So there are two main users for the excavated soils at our reclamation sites. The first one is the soft clay, which is the clay soils that are very soft and also wetter, which is mainly used for infill material from the seabed to above seabed level. And this soft clay has to be treated in order to accelerate consolidation and strength gain. And the second type is the good earth soil, where it is mostly used for internal containment bunds and also the topmost layer of soil for compaction. So misclassification of these soils may result in suboptimal use of the material and may pose challenges downstream. So there is a need for accurate classification of these excavated soils. So the current classification process is where we start off with limited borehole data and soil sampling of the site. And then we move on to the excavation activities itself. And next is to transport these excavated soils. And finally, we will conduct visual inspection and finally classify them into either good earth or soft clay. And the issue with this is that we receive thousands of truckloads a day, and lab testing of each truck is not practical, and also labor intensive. Hence, we want to explore new technologies to have improved this classification process. So this we want to develop a rapid soil classification method that is accurate, non-destructive, and also automatable. So instead of the usual current process, we shorten it over here. Okay, the animation doesn't play right. Okay, so anyway, we will substitute it with on-site rapid classification, and this will replace the visual inspection and also bring about objectivity and also more accurate and fast. So how do we do this? We explored the use of AI and computer vision to replace the visual checks at the staging grounds. So this computer vision process can be simplified into this four-step process, which is we obtain the image first, the image acquisition. Next, we process it, we segment the image, convert it to grayscale, and then thirdly is the image analysis where we quantify the texture of the image using grayscale co-occurrence matrix, and finally the last step is to decide whether is it good earth or soft clay. And the hypothesis is that it is possible to use artificial neural networks to classify these excavated soils into two categories with more than 80% accuracy and in less than 5 minutes. So from previous research, we have concluded that it is possible to use ANN, and we calibrated using image texture feature data that is obtained from representative soil images. And we have successfully used them to classify into good earth or soft clay with decent accuracy. However, the current system uses only captures data on the surface and does not account for possible soil layers that may be present under the surface. Hence, this presents an opportunity for us to evaluate other methods and to seek the feasibility of classifying the soil with depth using complementary soil parameters measurements such as resistivity and soil strength, which I'll go through later. So the brief overview of the steps is firstly, we prepare the soil samples. We have 4 tests, main tests. And the first 2 tests is the homogeneous soil mass, which is either good earth or soft clay. And for test 3 and 4, it's layered soil, which means there's one soil type on top and the other soil type below. And we will perform 3 main tests, which is the apparent resistivity, Cpt, and moisture content. And finally, we will evaluate the results. So over at the first step, we prepare the soil samples in this huge soil box, which is about 1.8 to 1.2 times 1.2 meters. And we fill it up to about 1,000 to 1,002 mm of soil. And for the 2 different soil types that we use for the good earth, is the one in orange, and for the soft clay, it's the one in blue. And you can see that for the soft clay, it is almost about more than 80% fines, and for good earth, it's much less. Yeah. So for the test setup, we can see that we have the soil box, and secondly, we have the sensors that are installed on this huge frame over here, and we will have actuators installed above these sensors to push them down into the soil box. So the first test that we perform is the apparent resistivity test, where we arrange 4 conductive probes in the Venus array, and we pass through current over the outer 2 electrodes A and B, and then we measure the potential difference between the inner 2 electrodes C and D. And from that, we can measure the apparent resistivity of the soil bulk under these 4 electrodes. The second test that we perform is the Cpt test, where we have developed a Cpt cone in-house, and data is captured every second. And the penetration rate is 8 mm per second, which is less than the standard 20 mm per second, because we want to ensure better sensitivity in the shallow thickness soil mass, because we only have about a meter of soil. And the final test that we perform is the TDR. So it's a time domain reflectometer, which is an instrument that sends a planar EM wave along the waveguides. And the velocity of this propagation is used to derive the what we call an apparent dielectric constant, which is a type of soil property. And this is used to estimate the in situ volumetric moisture content. So this is the instrument that we can use to measure the moisture content without doing the standard oven dry method. So over here at the results and discussion, firstly I'll go through the homogeneous soil, where in test 1 is the homogeneous good earth, and in test 2 is the homogeneous soft clay. So I think, okay, the graph is a bit contorted over here, but it's okay. Over here we can see that the one in orange is the good earth, and the one in blue is soft clay. So it is consistent with the moisture content graph over here on the right, because we can see that for soft clay it can retain more moisture, so it's high over on the right. And of course, because of that, we have lower apparent resistivity for clayey soils. And looking at the same soils, but it's the Cpt values, we can see over here is that it is also consistent with the soil type, which in the one on orange is the good earth soil, which is the sandier one, and it has overburden pressure. And on the other hand, the clayier soil in blue, it's almost constant throughout the soil, which is consistent with what we know for the soil. And on the right over here, the friction ratio, we can also see that the one in blue is definitely clay, which is about hovering 4 to 7%. And on the right, on the left, on the orange one, we can see that the sandier one is between 0 to 1%. So it's very clear and very distinguishable between the two soil types. And moving on to the layered soil, for test 3, it's the good earth soil on the top half and soft clay on the bottom half. And test 4 is the opposite. So we can also see over here that let's look at the orange graph. So the top half is higher resistivity because it's the good earth soil, and the bottom half is much lower resistivity because it's soft clay, where you can retain more moisture, and where you can see on the right also in the orange, where the top half is less moisture. So there's a inverse relationship between these two. And looking at the Cpt, the soil strength, we can see, let's look at the graph in blue, where the top half is soft clay, where we can see that the tip resistances for the clayer soil is much less. And at the bottom half, it's due to overburden pressure, so you see it increasing. And on the right, you can see the friction ratio. The top half is the much higher friction ratio because it's a clayey soil, and the bottom half it's the sandier one. So as also in layered soil, we can see there's a stark difference between the two soil types, good earth and soft clay. So these methods that we use are able to pick out this difference. And to have a short summary of the results, the first thing is that for homogeneous soils, these complementary soil parameter measurements were consistent throughout the soil depth. And for the second point is, for layered soils, these measurements are able to show significant differences between the top and bottom layers because they are the different type of soils. So for example, if the top half is soft clay and the bottom half is good earth, we can see that the tip resistances is much lower at the top half, where it's very much higher at the bottom half. It's very distinguishable. And this also holds true for the other parameter measurements that we have conducted. So in conclusion, what we have over here is that we have this newly developed rapid soil classification technique that's used to classify the soil into these two soil types, good earth and soft clay. And previous research using ANN was proposed, and we have conducted trials and used successful results, but this only accounts for the data on the surface of the soil. So this research that I've just covered is to expand the capability of this system to the depth of soil mass. So it's not just the soil surface, but also what's under the surface. And this field proof of concept has shown that there is distinguishability between the two soil types. Yes. So that concludes my presentation. Thank you.
Thank you, Jean, for your presentation. I think we cannot take any questions, but if anyone has any questions, they will email it to you. So we are going to proceed with the next presentation. Thank you very much again.
Thank you very much.
And our next paper is titled Numerical Study of Uplift Induced Levy Failure for the Design of a Centrifuge Test, and it is written by Veronico Girardi and et al. I think Veronico is here and she's going to present us his work. Yes, Veronico, the floor is yours.
Thank you very much. Can you already see my presentation?
Yes, we can see it.
Okay, I will proceed from here. So, good evening, everyone. I'm Veronica Girardi. I am a postdoc researcher from the University of Padova. And today I'm here to present to you the result of a numerical study aimed at supporting the design of a geotechnical centrifuge test. I've been working in collaboration with other researchers and professors from different universities all around Italy, and we are all brought together under the framework of a project entitled Resistivity. You can see it at the bottom of my slide, which is a project of national interest funded by the Italian Ministry of Research, Education and University. So the context, the motivation of the study lie in the awareness of us as geotechnical community that there is a widespread evidence of continuous and increasing occurrence of failures of water retaining geostructures. In particular, in this slide, I reported two pictures of recent events of collapse of river levees in Italy, but we all know that this is a problem that is very common all around Europe and also worldwide. For this kind of problem, we need, of course, as researchers and engineers to develop efficient risk mitigation strategies because we can't afford anymore the costs associated to the failure, collapse of portions, stretches of these earth structures. And the development of risk mitigation measurements starts with a deep understanding of the geotechnical behavior of these structures. So the particular objective of this work is actually understanding the crucial role of stratigraphy on levee stability under transient hydraulic loads, as reported in the center of the slide. I will be a little bit more precise in this. So we are interested in those instability mechanisms that arise when there is a preferential flow channel in the foundation soils of our levee. This happens when we have at depth a layer of sand, so coarse, permeable, which can create a direct interconnection for the flow from the river side to the land side. In this specific stratigraphic condition, two potential failure mechanisms can arise. On a side, the toe uplift and sliding macro instability mechanism, on the other, backward erosion piping. They both occur in a situation in which characterized by the fact that pore pressure can approximate the state of total vertical stress. In this manner, we can approach a state of zero vertical effective stress and thus static liquefaction near the toe area. These two mechanisms have been investigated before, but they are still partially unknown and very hard to reproduce, especially numerically, I may say. They are also very complicated in terms of prediction because we don't really know the spatial extension of them, if they are just localized near the toe or if they may end up involving an entire collapse of the levee section. So for this reason, we decided to investigate these two potential phenomena by using, in a combined manner, physical modeling by employing geotechnical centrifuge test and numerical modeling. The first approach helps us investigating favorable conditions for instability in our structures, analyze the entire failure event, which is not always possible with the available, let's say, numerical codes around, and also we can test monitoring instruments. On the other side, numerical modeling helps us as a support in a preliminary manner to the physical test. It helps us carrying out retrospective analysis and develop predictive models to be applied in other engineering contexts, geotechnical engineering contexts. So my presentation today is focused on the numerical analysis that support the physical test in the sense that they support the design. And in our team, we decided to test three well-known methodologies: the finite element method, generalized limit equilibrium method, which is preceded by a seepage analysis, and the Van method, which is based on a force approach. It helps us defining a factor of safety like the other two methods. But the benefit of it compared to the generalized limit equilibrium method is that it doesn't consider a pure circular slip surface. It can account for a straight part between the two circular sides, so a triple sliding surface more complex. These three methods help us try to reproduce the uplift and sliding phenomenon. On the other side, for the piping, in a preliminary manner, we did an assessment based on some empirical relations. We can start by going through observing what is the geometry that we decided to test and the material used. So as you can see in this slide, I report the geometry at the prototype scale, which is also the scale that we consider in all our numerical simulations, while the centrifuge is at the model scale, and we all know that the relation between the length of the two models is controlled by the factor of gravity scaling. In our case, it is equal to 50. As you can see, we decided to work with a Levy body composed by a mixture of two materials, TS and PON. They stand for, the first one, Ticino sand, which is a coarse to medium sand, as visible also in the granulometric curve in the graph at the bottom of the slide. And the second component of the mixture is Pontida clay. It is actually a clay silt with low plasticity. Both the two materials are particularly available in our areas and also used as construction materials. Below the flood embankment, we can find a first layer of Pontida clay, and under it a layer of Ticino sand, which is shaped with a sort of chimney shape in a manner that we can have this direct interconnection of flow from the river side to the land side. We are particularly interested in understanding the impact of the thickness of the Pontida clay layer on the overall stability, so we tested three different geometrical configurations with thickness 2, 2.5, and 3 meters. In this slide, I report hydraulic and mechanical models used in our simulation. In particular, soil water retention curve and hydraulic conductivity function are modeled with the Mualen-Wangenhoekten model. This is valid for FEM simulation and the seepage analysis prior to generalizing limit equilibrium method. For the Wangenhoekten model soil water retention curve, it was based on some experimental data, of course, while the hydraulic model is based on an estimation considering the Mualen law, and the saturated hydraulic conductivity were tested in the lab, like all the other mechanical properties and in terms also of classification. Concerning the deformative behavior, this is valid only for FEM analysis, and I report in this slide the three constitutive model that we use for the three materials. For all of them, the failure criterion is the Moore Coulomb, which is also used in the other two numerical methods that we use, considering drain parameter, friction angle, and cohesion, that comes from an extensive laboratory campaign considering triaxial consolidated drain tests. During the centrifuge test, we have two principal phases. The first one is the acceleration phase, where we go from zero gravity to the target gravity value. And during this phase, we assist to a consolidation process in our levee and in the foundation soils. This phase is followed by a phase in which the river level is rising. We want to make it rise to have a significant increase of pore pressure in the foundation soil. So at the numerical model level, the first phase, acceleration and consolidation, can be reproduced very well from FEM, but not in the other two methods. So when we want to reproduce this phase in FEM, we have to recreate an initial condition in which we start with a levee body with an initial suction of 5 kPa, which corresponds to the optimum water content, and the foundation soil are saturated. Then, to reproduce acceleration and the process of drying that occurs during it, we apply a constant outflow at the top part of the levee, and we impose a small value of river level, let's say on the river side, which is in the experimental test is just like a filling of water, to act in a stabilizing manner. The result of this boundary condition application is a distribution of pore pressure that you see in this slide. Is a little bit covered by the other graph because the animation are not really well functioning. I'm sorry for this. But the distribution of pore pressure, you can see it in the background, is the one that you can see here. And after the initial part, so acceleration consolidation, we can move into the rising water table phase. In this part, we had to design a specific hydrograph that guarantees the increase of pore pressure and a certain control of the pore pressure distribution and of the failure mechanism. So we decided to work with this hydrograph in step that grow of 1 meter each time, and each step remain for approximately 50 days at the prototype timescale. I report in the hydrograph also the let's say the period where FEM is actually working or functioning, so during the initial part and a part of the rising phase until non-convergence is achieved. And then generalized limit equilibrium method, which is comes after seepage. It is performed at every instant of the seepage analysis during all the river level rise. Concerning one method, this is not based on a boundary value problem, so we don't have a seepage analysis. We can directly impose some water level, and we decided to work with two different water levels, one that imposed, let's say, the distribution of pressure in Pontida clay, and one a little bit higher that imposed the water level in Ticino sand. This is based on an assumption of undrained behavior of Pontida clay with a concentration of high pressure only in Ticino sand, based on some previous experiences also in the literature. Let's see now the results. So first I want to present you the results of the FEM simulation in terms of contour of pore water pressure, incremental deviatoric strain, and plastic failure points. So as you can see, we have a progressive increment of the distribution of pore pressure, and in particular, when we pass from the river level of 3 meter to 4 meter, we notice that in terms of incremental deviatoric strain, we have a strong localization and concentration near the toe area with, let's say, an extension also on the land side and the river side. This has also a correspondence in the sudden, increment of plastic failure points near the toe. And this somehow suggests the onset of an instability mechanism. But we are interested not only in the FEM analysis, but seeing the overall results, comparing the results with the generalized limit equilibrium method and one method. So if we consider the first two methodology in the graph with letter A, we reported the evolution of the factor of safety with time and also the river level progressive increment. And as you can see, in general, generalized limit equilibrium method is suggesting the possibility of increasing the water level a little bit more before we reach factor of safety less than 1, so the condition of instability. And in both the methods, we can clearly see that the increase in thickness of the pond layer is acting in a sort of stabilizing manner and allowing to explore higher water level before the instability occurs. On the other side, when we go to have a look into the one method results, only the case with thinner pond thickness reach a certain instability situation with factor of safety less than 1, while the other two geometrical configurations seem to not show a potential instability, probably due also to the approximation that we made in terms of pore pressure distribution. I will go briefly through the piping assessment, which has been done with 3 different criteria that are the Bly, Lane, and Selmayr criteria. In all of them, we had to compute the minimum seepage length and compute the creep coefficient based on the properties of the sand layer. Additionally, we assume that the pressure F is different than 0 at the exit point. This is based on a recommendation that is popular in the Netherlands. And we calculate the critical head with these 3 criteria. So I'm going to show you now the result, and you can see them together also with the previous results. What appears is that if we just look at these criteria, Selmayr method is giving like lower critical head compared to the other 2 methodology. And overall, they are a little bit lower compared to the results that we obtained with the numerical methodology, the numerical simulations. The 3-meter pond thickness, the one bigger, is actually guaranteeing higher water level, which are still not as high as the Levy crest, of course, so we have a certain margin, of potential additional rise. So we believe that the potential optimum geometry that we are going to test is the one with puntida thickness equal to 3 meter. So to conclude with this study, I hope I was able to show you how we work toward the design of a geotechnical centrifuge test by defining the geometry, the foundation layer thickness, the selection of hydrograph that highlight critical hydraulic heads with potentially trigger failure. And to conclude, I want to show you the suggested location of the monitoring instruments during the centrifuge test that we believe is going to be efficient if we place a series of miniaturized tensiometer in the Levy body and near the toe, a series of piezometer in the foundation soil to actually monitor the rising of water pressure in the sand, but also in the puntida clay, and LVDT and rototransitive transducer near the toe area and also near the crest to monitor displacement and deformation during the test. So thank you for your attention, and if you're curious about the development of this project, here I reported the link of it, which is an ongoing project, and we hope we will show you further results soon.
Thank you, Federico, for your nice presentation and your timely presentation. Thank you again, and now we are going to our next presentation. It is by Hande Yumuk and Gürkan Özden, Influence of Excess Pore Pressure Development on Inertial Pile Response, and it will be presented by Hande Yumuk. And yes, please, Hande, can you make your presentation? Hande, you are muted. Yes, we have seen your screen, but then gone.
Could you see the...
Yes, now we can see the screen and we can hear you. We are listening to you. Thank you.
Hello everyone, this is Hande Yumuk. I'm a graduate student at 9 Eylül University. Today I would like to present you our study about the influence of excess pore pressure development on inertial pile response. This presentation is part of my Master of Science thesis. The outline of my presentations is given here. We are going to start with the introduction, then I'm going to talk about the scope of the study, the statement of the problem, materials and methods, and 3D numerical analysis, and finally conclusions. As we talk about excess pore pressure's influence on inertial pile response in general, we talk about liquefiable soils surrounding pile foundations. During earthquake shaking, liquefaction and pore pressure buildup in cohesionless soils around piles may cause the natural frequency of soil pile systems to decrease, the vibration amplitudes of piles to increase. In extreme events, superstructures collapse due to large pile movements. The effects of inertial loads on excess pore pressure generation mechanism in cohesionless soils were investigated, as I said. Considering these effects in our study, we are going to see pore pressure development and soil reaction. Let's show the influence of excess pore pressure development on pile response with the help of an analytical model. For instance, in this slide, we see the model by Kagawa and Kraft. In equation 1 over here, reaction the soil reaction is a function of soil stiffness and displacement rate. However, it should be mentioned that in liquefiable soils, the influence of viscous damping is always negligible, and soil hysteretic damping as a result of nonlinear soil response is much more important. We can see the backbone curve can be established by step by step until we obtain modified backbone curve, and excess pore pressure influence is incorporated into backbone curve using excess pore pressure ratio. Although analytical models such as the the one given in this presentation may be utilized to incorporate the influence of both free field and near field excess pore pressure generation. The model may also be utilized to define excess pore pressure generation due to inertial interactions solely. Here we can see the final form of Soy reaction as given equation 9. Now the question is to obtain excess pore pressure as a function of soil density, as a function of loading frequency, loading intensity, and the number of cycles. We try to obtain these within the scope of this study. However, I should mention that the results represent the preliminary results of my thesis. As the study essentially targets pyre response in saturated cohesionless soils, Wildlife National Geotechnical Instrumentation Site was chosen. University of British Columbia sand model was the material model due to availability of calibrated UVC 3D PLM models in the literature. Soil parameters assigned to the finite element model are given in the table. The pile was modeled as an elastic volume element using non-porous material model. There is a single pile that is fully embedded in loose liquefiable soil. Two modeling approaches are considered in the study. Model A is a full pile-length model, and Model B is a slice model to represent 1 meter thick cross-section of full model. We run the slice model because it's useful to control boundary conditions. We just restricted the pile and we let it displace only y direction, which is the loading direction. In these terms, we avoided the rotation and we just observed the changes in soil response as a result of lateral pile displacement. And the mesh quality was reasonable in the finite element models. The dimensions of the models can be seen in the figure. The slenderness ratio of the full-length pile is 25. In the analysis, we employed 10 loaded wedge elements. The interface coefficient was 0.67. We run monotonic and cyclic analysis under drained and undrained conditions. The loading intensity varied between 25 and 300 kilopascals in a monotonic analysis and 25 to 200 kilopascals amplitude with 1 and 2 hertz frequency in cyclic analysis. Here we can see the result of excess pore pressure as a function of loading intensity just in front of the pile. Over here, horizontal strain values reach the 1.2%, which is high enough to trigger plastic soil response around the pile. The pressure is denoted by a negative sign, and a positive sign means negative excess pore pressure as a result of dilative soil behavior. Excess pore pressure reached 100 kilopascal. Excess pore pressure exceeded initial effective stress. This is common in the literature. Nearby the pile surface, we observe quite high gradients. The initial effective stress was just 37 kilopascals. We can see the 3 folds of excess pore pressure increases were recorded. We can see that especially at large loading intensities, the soil next to the lateral displacing pile liquefies for sure and gets into the probably viscous liquid state. As we go away from the pile, excess pore pressure development diminishes quickly. We can see that at smaller amplitudes, initially there's a contractive behavior. However, after small strain amplitudes, dilative behavior governs, and the pore pressure development quickly happens to be negative. And the 3.8 pile diameter away from the pile surface, we see a completely dilative response, and the excess pore pressure magnitudes were quite negligible. The PQ diagrams as plotted here also show the influence of distance and loading frequency. 1B away from the pile, the soil gets closer to failure, but away from the pile, we see the soil response is of dilative nature. as we compare 1 and 2 Hertz loading intensities, we can say that the soil becomes weaker at larger loading frequencies. There is almost a 30% change difference between 1 and 2 Hertz responses. The previous slide is from full pile length analysis. Over here, we presented a similar graph, this time from pile section analysis. Similar soil responses in the PQ diagram were obtained. However, they are not exactly the same. This is probably because the excess pore pressure migration in the three-dimensional model from higher gradients to lower gradient zones is not present in our pile section analysis. But the comparison reveals that the pile slice model can also be utilized in soil-pile interaction analysis. Over here, we see the influence of loading intensity. As we discussed earlier, loading intensity gets higher, the dilative soil response becomes more influential, and the soil does not get closer to failure as it does with lower intensity loadings. The 25 and 75 kilopascal loadings are more critical in terms of soil response. As we see, finally, we present soil resistance versus pile displacement. This is from the pile slice model under drained and underhead conditions, and we compare them with the American Petroleum Institute model for sandy soils. Here, we see that especially drained monotonic analysis match perfectly with the API model. And in underend cases, due to excess pore pressure development, we see the smaller soil reactions. There is a threefold decrease in underend monotonic cases. As a conclusion, we can say UBC 3D PLM model can be utilized. Excess pore pressure accumulation can be obtained. However, we should mention that the UBC model may be quite sensitive to boundary value problems. Pile section analyses are found to be applicable to inertial cyclic loading cases. Both full length and pile section models show that high pressure gradients take place at the soil pile interface, and a dilative response occurs at larger loading amplitudes. Shear results indicate considerably pore pressure develops within the surrounding pile. Inertial soil-pile interaction reduces soil resistance. And here are my references, and thank you for your attention.
Thank you, Anja, for your presentation. And I have seen that there is a comment part in the screen, but there are no questions and nothing in that part. So thank you. And we are going to proceed with our next paper. However, our fourth paper in the list, the presenters are not here. So we are going to the next one, and we are going to do topics of emerging subjects in geotechnical engineering. As far as I imagine, we are still in Izmir because the paper is written by Esra Güneri and Yeliz Yükselen Aksoy, and Esra is going to present the paper for us. It is titled "The Shear Strength Behavior of Perlite-Added Sand Bentonite Mixtures Under Room Temperature and Thermal Cycles." Yes, Esra, we are listening for your presentation. We cannot hear you. Okay.
Hi everyone. I prepared my presentation as a video, but I can start.
I think it has started, but there's a problem with the sound, maybe.
1 minute.
Or you can just share your screen, and I think there's a problem with the video, and you can just share your screen and then present again. Okay?
Okay.
Our director says that slide is not, it is working as a slide, video is not working. Share screen and then your presentation. We are waiting, no problem.
Thank you.
You should share your entire screen.
One minute.
Have a good day. I'm Esra. I'm a PhD student.
Can you see the presentation?
Today I
No.
will share.
We can hear the sound, but not see it.
Why didn't it? I don't understand.
I don't. Share screen, full screen, and
Yes,
share.
I did, but
Oh, I don't know. Then maybe we can continue with the next one and then turn you back. Is it possible? Is Ivan Menisek and Martin Menisek, if they are here, we can proceed. Click your screen. Our director says that. Can you see the share screen button?
yes, I see. But I didn't see the PowerPoint presentation.
Is it open at the back? If it is possible, Göksel Bey, we are, let's begin with, oh yes, and your presentation, yes.
Can you see?
And yes, we can see it, and then
And-
you can just make it to the slideshow, and it will be okay, I think.
And I start.
Have a good day. I'm Esra. I'm a
Now we
PhD
can
student
see.
at Have a good day. I'm Esra. I'm a PhD student at 9 Eylül University. Today I will share with you the results we obtained from the notification titled Shear Strength Behavior of Perlite Added Sand Bentonite Mixture under Room Temperature and Thermal Cycles. In my presentation, first of all, I will briefly talk about the interaction of soils with temperature and the methods I use in the tests and the results I obtained. As you know, the demand for sustainable energy sources and structures is increasing due to the increasing population and the need for energy. Solid waste and nuclear waste storage areas, buried power cables, geothermal energy plants, heat piles are the structures and the facilities that cause temperature change in the soil. Materials to be used as buffers are needed in order for the soils to maintain their engineering properties against thermal effects. The main energy structures that cause temperature change in soils are heat piles, buried power cables, solid waste and nuclear waste storage areas, and geothermal energy facilities. The temperature change in all these structures affects the properties of the soils foreseen during the design phase. Many studies have been conducted to examine the behavior of soils in the presence of temperature. Although there is still no clear view on some issues, some conclusions have been reached in general. For example, studies show that as the temperature increases, the amount of volumetric deformation increases and permanent deformations occur. In addition, it is one of the main findings that hydraulic conductivity increases due to the decrease in viscosity as temperature increases. In this study, we aim to obtain high temperature resistant soil material by adding perlite additive to sand bentonite mixture. Perlite is a highly porous material of volcanic origin with a chemical structure predominantly made of silicon dioxide. It's also frequently used in thermal insulation. Table 1 shows the properties of the materials used in the experimental studies. In addition, images taken with XRD and scanning electron microscope at room and 80 degrees temperatures are given. It is observed that from these photos, perlite has a highly porous structure at room temperature, and these voids separate further under high temperature and the material loses strength. With our compaction tests, we determined the optimum water content and maximum dry unit weight of 20% bentonite, 80% sand mixture, and perlite-added sand bentonite mixture. For direct shear tests, the device you see in photos was used under room temperature and thermal cycle. In the test carried out at room temperature, the samples were allowed to be cut under 3 different normal stresses. In the test under thermal cycling, the samples were heated for 8 hours during the consolidation stage at 80 degrees and cooled for 16 hours at 25 degrees and then left to be cut. Black membrane-like elements specially designed for the shear box, heat rod, and pipes against the possibility of water evaporation were used. In addition, the tests were carried out under a stress of 196 kPa for each sample. The compaction test results show that the perlite additive has the effect of increasing the optimum water content of sand bentonite mixture and reducing the maximum dry unit weight. Because perlite is a very light additive with a dry unit weight of 2.9 kilonewtons per cubic meter and has a high water holding capacity. The direct shear test results of the mixture show that as the perlite content increased, the internal friction angle of 20B ATS mixture increased and the cohesion value decreased under room temperature. We can explain this behavior as perlite has selenol groups on its surface, and selenol groups are held by the clay surface by binding to hydroxyl groups at the edge of the clay plate. Thus, the shear strength of the sand bentonite mixture increases with the addition of perlite. The direct shear test results of the mixture show that as perlite in figure 5, the shear stress horizontal strain graph of both room temperature and thermal cycling test results is given. As can be in figure 5, the perlite additive had an increasing effect on the shear stress of the additive-free mixture under room temperature. Because selenol groups on the perlite surface were held by the clay surface by binding to hydroxyl groups at the edge of the clay plates, and this exchange causes increase in shear strength. However, this effect was not observed under temperature cycling. The fact that the voids formed in the structure of perlite with increasing temperature are irreversible when the mixture is returned to room temperature, and it causes decrease in shear stress. On the other hand, when the same mixture is taken into account, the fact that the stress value under the temperature cycle is higher than at room temperature can be explained this situation by the increase in ductility. In other words, Because of ductility, the mixture can sustain more deformation under the applied normal stress in the presence of temperature. Also, perlite additive decreases the shear strength of the mixture, but 20% perlite reach higher strength than 10% perlite additive under thermal cycle. The lower bentonite ratio in the 20% perlite added mixture causes the higher shear strength when compared with 10% perlite added mixture. In addition, the porous structure of perlite is one of the main reasons for this decrease in strength of the sand bentonite mixture under thermal cycles. According to results of this study, when perlite additive was added to 20B ATS mixture, it increased the optimum water content while decreased the dry unit weight of the mixture. The direct shear test results performed at room temperature revealed that perlite has an increasing effect on the shear strength of the mixture. In addition, the results of the direct shear test performed under the temperature cycle show that both perlite ratios have a reducing effect on the shear stress value of the mixture. The shear strength improvement effect of perlite on sand bentonite mixture was found to be significant under room temperature but insignificant under thermal cycles. Thank you.
Thank you, Esra, for your presentation, and we can hear it and see it as well. And now we are going to proceed with our next paper, next presentation. It is written by Ivan Vanisek and Martin Vanisek, the role of building information modeling for different phases of geotechnical investigation of the transport infrastructure. I think they are here. Martin Vanisek is here. Yes. You are muted if we can see your... yes.
Yes, hello.
And by the way, I have been warned that the presentations are limited to about 10 minutes. I will be very happy if you can finish it in 10 minutes. Thank you.
Okay, I'll try my best. Okay, hello everyone. I will present on behalf of us two. I'm Martin Vanicek, and I will be talking about the role of building information modeling for different phases of ground investigation and for the design of transport infrastructure. Okay, so building information modeling is in principle a process reacting on up-to-date demands on digitalization increase. BIM is shared or shareable source of knowledge about a certain facility, creating confidential base for decision-making process during all of its lifetime cycles, defined from the first conception or study to its demolition or decomposition of the structure. In other words, building information modeling is a process for optimization of the individual phases of engineering structure, from the phase of the first study through investigation, preparation, through all the phases of design, toward the execution, and finally to the use of the structure. BIM, in a sense, is a 3D computer visualization of the engineering structure, and where the structure is divided into the smallest details. This is much more easier for 3D model of buildings. More complicated is for the civil engineering structures, because there is not so many of individual smallest structures. And the most difficult it is for ground, within which the structure is in interaction. Oops. So where the geotechnical engineering is within the BIM process? We all know that all structures are in close interaction with ground. And for the buildings, it's the load from the superstructure which is transferred through the ground to the ground via the foundation structures, as it's shown on this figure on the right hand side. So the superstructure and foundation and the ground itself all together are one structure. Therefore, a ground model is a very essential part of the whole structure and in fact the starting point. However, the ground properties are very unhomogeneous because it's coming from the natural material and it can change very strongly within its position, and the determination of the ground properties are connected with very large uncertainties. So just to show example of such a BIM model for the civil engineering structures, so the arch dam can be one of the nice ones. Because of transferring the very high hydrostatic pressure into its foundations, very often nice good rock which is on the foundations and also on side, so therefore abutments, and effectively it's the best for the very narrow canyons or gorges with very steep slopes. So you could see it's one of the important parts. For a transport infrastructure like motorways or railways, geotechnical structures are even more important because, as shown on the figure below, you have foundation structures for the, let's say, for the bridges and other structures. Then you have the air structures, which is generally the embankments, cuttings, and the underground structures like for tunnels. So in fact, we can say we are constructing on ground the bridge, we constructing with ground, so the air structure, and constructing within ground, which is the tunnels. So, and here the geotechnical model is very much in the heart of the BIM model. So this pinpoints where the geotechnical modeling or geotechnical part within the BIM model is. If we talk only on the foundation structures, like for buildings, the BIM model is a large center for the structure itself, and geotechnical structure is minor part for the foundations themselves, like on the figure on the left. And on the other hand, for the airs and underground structures, the geotechnical structure itself is the heart of the BIM model, and all the others are just helping around. So it's the figure on the right hand side. Here we can show the logical scheme, how it works together with Eurocode 7 design according to Geotechnical Design Report. At the beginning, on the left, you have the ground investigation report, which prepares the data from the burrow pit for embankments. You do the lab testing, you get the properties. For the other parts, cuttings and tunnels or foundations, you get the ground investigation within the place, get the properties just from few boreholes through investigation points, you get some idea how it looks like, and you get the properties from the measured values from in situ testing, or you can get other values from lab testing. Usually gets measured, or indirectly you can derive the data. Then we move from the ground investigation and ground model towards geotechnical design model, where we get, or we have to, those measured and derived data or values transfer to using a cautious estimate approach towards the characteristic values which are specified in the middle of the figure. And then this is essential part for, or starting point for, the calculation model, which can even more simplify the situation. We can use either analytical methods, semi-empirical, or even, and the most advanced are the numerical methods. And at the end of the day, when we get to the construction site, during the construction, we control the properties either for the embankments, back again to the lab testing for, let's say, proctor tests, to find out if the compaction was correct, or when we are in the cutting, we take the samples and compare it with the ground investigation, what we found out, and to confirm if it's right or wrong. So now we can talk about how to determine the ground model, or where it comes from. It's, as it was shown already on the previous slide, it's coming from the ground investigation, and it's step by step improved during the design of the geotechnical structure. Because we have to take very important care what we do during the ground investigation and the design, and both of it are very much connected to the structure risk. So, in a sense, all partners of the construction process, starting from the investor or owner of the structure, the people who are responsible for the ground investigation, down to designer of the structure, and at the end of the day, also to the contractor, they should work together. If not, it can be a disaster sometimes. But if they work together, they can decide the right ways how to determine the ground properties to significantly reduce the risk of the structure for the structure. What's important is to get the right distribution of the investigation points, both horizontally or aerially and vertically, using either boreholes, some dynamic testing, in situ testing, geophysics, whatever, and also to perform the right lab and field test, so we get the right information about the ground, and so we can much more easily, without big risk, to solve the problem. Here we're trying to show what are the links between different stages of ground investigation as in line with the geotechnical design. Of course, at the beginning, we have a desk study for ground investigation. It's relevant for the study or idea of the project. Sorry. Then we go to preliminary GI if the project gets start. Then we do the first design, which is generally to place the structure in the environment, in the place. Then we do a detailed design to design it and to get a building permit. This design has to be reasonably detailed. If then we found out that the design is better to be modified, usually when the contractor gets on board, we have to do the supplementary GI to get additional information to mitigate additional risks. And maybe the last stage of the ground investigation, we can call it confirmatory ground investigation. It's done during the execution of the structure, when we document what we found and during the construction. So the first three phases of the ground investigation for transport infrastructure are generally divided as this was shown on the previous slide. The first one is a desk study. It's just to find out from historical data, existing maps, what site walkover, the feel for the site, to get initial information about the geology of the site, and to be able to get enough information to say if it's worth to do the job or to design the structure or not. It can be also used in a very, very quick way for the environmental impact assessment as well. The preliminary ground investigation is generally to get information about reasonably larger area to make sure that we cover all affected soil which would be affected by the structure or which can affect the structure. We usually call it zone of influence. So we need to know horizontally, vertically, where to the extent of the investigation, which can be seen here on the topper figure, how the settlement of a reasonably large embankment will be influencing below to define the settlement, for example. Or another figure is the slope stability, what we need to know, how far we have to go with the investigation to get enough information for it. It's not only the geologists who define it. It has to be there, the geotechnical engineer, to know what they are going to design and to give ideas or information what we need for the design as geotechnical engineers. So for the preliminary ground investigation, we do different exploration points, boreholes, trial pits. We can do some geophysics methods as well to get the initial model. And based on what we obtain, or if we select something for the testing, then we can get the first geotechnical model, and we would try, based on the collected data, to divide the zone or the zone of influence to so-called quasi-homogeneous layers zones. What it means is to get the areas of similar geotechnical properties for those zones, and it will be shown on the next slide how we can determine that. And in this part, or in this phase of ground investigation, the quasi-homogeneity can be demonstrated just on the index tests or descriptive properties of soils or rocks. So generally the simplest idea is to, when you compare the, which is shown on the left hand side, the composition of granulometry, if we have one set or two sets of data, that's usually for the coarser soils. If we have finer ones, we can go to the middle figure or even to the right hand side figure, where we can determine if we have on other properties like index of plasticity, to find out if we have one or two different sets of data and therefore soils. So from the results of this preliminary ground investigation, we can more or less specify vertically and horizontally the traffic route or the center line of our transport infrastructure structure. We can determine where we will have fills or embankments or cuttings, where even tunnels will be, where if the embankments would be too high, then what structures we can do and how to found them. It's also used for the preparation for the planning inquiry. Can be used to determine the ratio between the excavations and fills, especially to take into account the quality of the excavated material, if it's possible to use it within the embankments or not. And generally we try during the design to make it equal, so that we would not have any need to store additional soil or rock somewhere else. So we have to take into account the sustainability of the construction. Also, it's price-wise what we need to purchase the land underneath the transport infrastructure project. And as I already mentioned, this is sustainability in terms of lowering the needs for land take, energy consumption, and use of natural aggregates or natural resources. And of course, we need to know, or we need to get the right information how we can get, or what we have to do during the next phase of the design ground investigation. So design ground investigation then provides sufficient amount of relevant data on the rock and soil environment, which is needed for the design of a geotechnical structure, so it shall be safe, economical, and also environmental friendly. We need sufficient amount of testing and properties determined for each quasi-homogeneous unit, so we can do either statistical evaluation, or if it would not be a very important structure, then at least some engineering judgment on the right properties to be selected. So here is a very high demand on quality of sampling, amount of it, and testing, both in lab and in field, in situ. And of course, we have to determine the places where the geotechnical risk is the highest. Just to show an example of the BIM model for the real structure of the embankment and its subsoil, can be this 3D view of embankment of soft soil where we have different soil layers, different boreholes. You can get there vertical drains to speed up consolidation. You have there data for fill material, and if needed, the embankment can be reinforced, so we need data for the reinforcing elements like geogrids. So all these information has to be included within the BIM model, so the designer will be able to design it, and when it transferred to the owner, they can maintain it, and if something goes wrong, to be able to use it for the help of the other for the future. So generally, this table summarizes all the steps based on the, as it is the first column, on the phase of ground investigation, what we get, and where it goes. And we get to the conclusion of our presentation. So to accept the BIM model for geotechnical engineers is a really nice chance to get more in control and to get a higher profile for their profession. Once it's accepted properly, it can help the optimization of the ground investigation, to the design, and also to the structure execution, especially with respect to the risk the structure is associated with. Geotechnical structures can cooperate with the information with the other partners within the process, and can be big advantages. As I already mentioned before, the values are stored in the model. You can refer back to it even several years later to find out if something will be built around, or there will be some other issues, maybe some accident, you have to repair the structure. You would know how it was built, what the properties of it are, and what was used for the construction. So it's very important. Generally, the BIM model is very important, not only during the design process, but as well during the utilization or use of the structure, very much toward the future. So I would like to thank you for your attention, and would you have any questions? I would be very happy to answer them.
Thank you, Dr. Vanacek, for your presentation. I think we have no questions, but it is an interesting topic, so I'm sure that they will email you their questions so that you can answer them. And we are going to proceed with our next presentation. Actually, we have an absent paper. This next paper is also absent, and now it is our last paper. It is written by Karakaş, Ülker, and Taşkın, and Dr. Can Ülker will present us the paper, which is titled Prediction of Load Capacities of Closed-Ended Piles Using Boosting Machine Learning Methods. Can Hocam, if you are ready, yes.
Yes, can you hear me?
Yes, we can hear you. And the screen is okay. Okay, the floor is yours. Thank you.
Okay, thank you very much, Professor Unutmaz. I will try my best to, go through the slides as quickly as possible. There's not, I guess I'm the last one, but hopefully not the least. As we have also seen earlier this morning covered by both by Professor Lacaste and Professor Foon in their keynote speeches, my talk is going to be about also machine learning methods and their application to foundation engineering. Well, in this case, actually, I'm going to just go through the introduction and then talk about some of the machine learning methods that we have used in our research project. Mainly the boosting machine learning methods, what was called the subset of nonlinear machine learning methods. And then once I talk about the database, which we use to teach these machine learning methods, which also consists of both confirmatory test data and full-scale pile load test data. Then I'm going to present you the results of the training and testing of these algorithms and hopefully the whole validation process. And it's going to be covered by the results of the analyses, the predictions, and then I will spend some time talking about the newly emerging method called Shapley method, which is used to explain the interpretability of the problem at hand using machine learning methods. The problem is that we would like to predict the axial load capacity of piles, in this case, closed-ended piles. For that, we rely on both pile geometry and confirmatory test data available in that particular field. And as you know, confirmatory test is a very valuable field test, which is also heavily relied on modelers who use machine learning in their projects to make predictions that are perhaps in the future going to take place the classical methods, or at least be used along with them to understand the whole variability or the stochastic probability associated with soils. Why we use CPT? Because there is a whole bunch of them out there in the field. There have been many tests done already by many companies or research groups. So it's out there. And then, as you know, in order to be able to have or make good predictions using machine learning methods, you need a very large database. The larger database gets, the better your results will get. So since we have many CPT, results available, why not use them? And as you know, CPT both give us information about both the physical properties and engineering properties of soils. So it's a very valuable test in this regard. As far as using CPT to identify the pile load capacity, we have a number of classical methods, as you can see in this slide here, available. So if you would like to use CPT with the in your machine learning calculations, analyses, then you better have some preliminary calculations with some of these methods and have an idea about what to expect as a result in terms of load bearing capacities, depending on the soil type, obviously. So I'm not going to talk too much about the details of the machine learning methods we have used, but to give you an idea about this emerging topic, and it is indeed an emerging topic in not just in geotechnical engineering, but in civil engineering, in any knowledge engineering fields as well. So there is both linear and nonlinear machine learning methods. And leaving the linear methods aside, nonlinear methods are mostly black box methods. However, they give, as long as you know how to use them, and you have a large enough database, they give you quite good predictions. So we can talk about both boosting methods type nonlinear methods and other nonlinear methods. We have seen people use many times what I mentioned here as other nonlinear methods, such as the relevance vector regression or Gaussian process regression, etc. However, we wanted to go in a different direction in this research and use what is called boosting methods. Extreme gradient boosting, light gradient boosting, and categorical boosting are the three boosting methods that we have used in our research. The difference between these boosting methods and other nonlinear methods is that these boosting methods provide high processing speeds, as you can see here, with that can be used in processing of large data, and in the meantime, also they need less computational resource, so they're not computationally costly. So it was quite efficient, and also it allows parallel processing as well in this phase. They're 10 to 20 times also faster than other typical nonlinear methods. So as far as database, we have both used driven and drilled shafts, driven piles and drilled shafts, as long as their ends are closed. So it's called closed-ended piles. And about 219 case records are used from 52 different locations, where all the piles were loaded in compression, and in the paper we also, I believe, provide the sources of this database, because those of you who are working in this in machine learning field will know that it is hard to gather data. You spend weeks and months to gather data first, and it has to be consistent, it has to be full. You have to have the full information associated with all this, and then you can do the analysis. Believe me, analysis part takes less time. It's amount of time. So, so having set the database, we need to determine the input features, and in this case, we have used both pile length and cross-section area as the geometric features of the pile. And on the soil side, we used cone tip resistance at the base of the pile, QC end, and the average cone tip resistance along the pile, which is QC average. And according to our analyses, and also, which are also supported by Shaheen 2010 study, the sleeve friction measurement is less dependent on the capacity, or in other words, has lesser effect on predicting the pile load capacity, which is, if it is associated with machine learning in this case. So we leave it aside. And when you what we mean by the cone tip resistance at the base of the pile, which is a QC end, it's written or identified as the geometric average of the dip resistance along the influence zone around the pile. So, and then we have to define what influence zone is. It is determined based on a number of conditions, depending on whether the soil is weak above or weak below, or strong above or strong below the tip of the pile. From 4D, the dimension, the diameter of the pile, 4D below the pile tip to 8D above the pile tip. it was the case if the soil above the tip is weaker than the soil below. So this is a summary of what I was just trying to say here. Then I wanted to put this slide here too, so that this is the zone of influence where we have decided to use the QC or define the QC end bearing of the CPT test around the tip of the pile. And again, as you can see, it's different for homogeneous soils as it is for from weak to strong or from strong to weak transitions of the soil. So the shaded areas are the considered influence zones, and same as for the average QC resistance, the tip resistance, and the sleeve friction FS. Although, like I said before, I mentioned that I present the FS average here. We did not consider that in our further machine learning calculations. So what we did here is that there should be an animation here. I guess it doesn't quite come up, which is fine. Let me quickly explain what's going on here. We have separated data into 5 folds using the what's called K-fold cross-validation procedure. It's just 5 subsets of the whole database. And then in the, so this is the testing and training phase. And so you use one of these folds or subsets for testing, and then use the rest of the 5 folds, the rest 4 folds in training. So once you train your machine learning method with the database using the 4 folds, then you test the outcome with the left of 1 fold. And you do this for each fold. Meaning if you, for example, just pick fold 1 for testing and the other 4 for training, and then once you're done, you move on to fold 2 for testing and the other 4 folds for training. So this way you work your way through all the folds and then just finish the training phase. And I guess this slide explains what I just trying to say here. If you, for example, pick fold 1 for testing, then it's the input. Once you determine your input features, you can embed them in your machine learning models. In this case, the 3 boosting methods, and then come up with predictions. Then once you have predictions, you can compare them with the in terms of pile load capacity with the actual capacities measured in pile load tests. So that way you know whether your training has been successful or not. And then how do we quantify this success? By using the coefficient of determination R square and the relative error measurements. And then strong correlations have been reported in literature for R square greater than 0.64. This slide is the algorithm that we have come up with in developing our computer code, and basically the summary of whole machine learning process, which is, I guess, typical in any other machine learning feature too. I'm not going to spend too much time here. So before moving on to the results of these boosting methods, I would like to talk about this fairly new concept called Shapley additive explanation method. Especially, it is quite original topic or a method, I should say, that is recently being applied to civil engineering problems, and especially geotechnical engineering problems with high variability in soil properties. So SHAP is short for Shapley additive explanation. Yes, it is not the Shapley's SHAP. It is the SH of Shapley, A for additive, P for explanation. Yes, it's interesting, but that is how it is. It provides the necessary interpretability of the tree-based algorithms and explains how the model predicts a value through the feature selection methodology. So basically, it allows you to quantify the quality of your prediction, which is based on a number of input features you use, right? So, and then it tells you whether this has been, whether the use of those particular input features was a good idea or not. long story short, okay? So, like I said here in the bold here, that whether an input feature of a given database is sufficient to provide the most accurate prediction of the output. So you don't know what input features will be necessary to be used to give you the highest quality predictions or accurate predictions. You just pick a number of different soil properties, for example, and then try to come up with one ultimate final value. So Shapley allows you to identify what input features are gonna be sufficient and necessary to have a most accurate prediction at the end, in short. And then also, once you do that, in the end, it can also potentially lead to new feature combinations. So, for example, you start with 5 features, 5 input in the beginning. Then in the end, you decide your Shapley analysis gave you the results of, say, like 3 input features will be sufficient, not 5. Leave out the rest 2. And then you don't know whether that's going to be the case. Maybe 5 will be the ultimate value, right? So then the idea is that to be able to come up with all this thing here. I don't know what's happening here because of the formula here. It looks weird. It's not that important anyway, so it doesn't matter. Don't have to worry about the equations. It's just that the Shapley, the Shap exhibits interpretability with the effects of features on each observation. So you account for the effect of input features on each observation of the data in the database, and then you go with the final outcome. But then the methods themselves, the machine learning methods themselves, do the job too for you. You can, some of you, again, those of you who are familiar with machine learning process, the machine learning methods themselves provide this feature interpretability, which is called Genie Importance. That's what we call Genie Importance. So the importance given to the input features by the trained machine learning models is also calculated in our analysis. Then we compare them with the Shapley and decide whether they match as far as the inclusion of input features or not. So let's talk about the results quickly. I'm gonna quickly go through the results. First, obviously, we use the boosting machine learning methods, and we wanted to present their outcome. So about 80% of R² is what we got using these 3 boosting methods. And again, we wanted to predict the ultimate load capacity of closed-ended piles. So 80% R² accuracy is okay for this type of problem, considering the size of the database we have used. And then you see these statistical parameters here in terms of the standard and mean, maximum, etc. for all the features. And then QU is the ultimate load-bearing capacity of the pile, which is the output. So the standard deviation and then the mean, the ratios being close to 1 means it's the training has been okay, has been good. Again, once we have used the machine learning boosting methods in our analysis, we wanted to use the Shap to get their Shap values. So what you see here is that the number of bar plots for the 3 boosting methods and another method called RF, random forest method. I know I didn't tell you about that before, but I wanted to put here mainly because random forest, if I'm not mistaken, Professor Lacoste also mentioned that in her analysis, machine learning analysis. I may be wrong, but it's quite often used in our field by modelers, and it gives pretty good predictions. And in a prior study with one of my former master's student, this Altınok and Ülker 2021 study, we have determined that RF, the random forest method, provides the most accurate prediction for the same closed-ended pile database. So I wanted to use that to compare it with the boosting methods here. So what you see here is that the blue bars show the Genie importance, the importance provided by the methods themselves in terms of the features, and the orange ones they give us the Shapley prediction. So they match for different input features, and the input features are length, area, and the end bearing and the average end bearing. So the cross-section area looks like is the most influential input feature towards predicting the ultimate load bearing capacity, cross-section area, right? And this is validated by both the Genie importance values and the Shapley method. Okay, so that's kind of a good approach, a good result that we have obtained in this case. Whatever you do, you have to include the cross-section area of the pile, which is understandable. What you see here is that now we have taken another step further to determine what we call global interpretation of the input features, interpretability, or their use, their effect on the outcome, final output. The global interpretation is that so what you see in these plots is the global means like the effect of each feature on the overall output. So what you see here on the right hand side of graphs is basically the clusters and number of dots for each input data. For each data in the database corresponds to a point or a dot in the graph. And then, so the Shapley values are given on the x-axis and the feature values from low to high given on the y-axis. So you see a number of clusters get together here because there may be more than one data obtained in the database that has the same Shap value, right? Or the same importance that exhibits the same importance. So the larger the x-axis scatter that of the input features, area, length, QC, and QC average, means that feature is more important for you in you're making your own prediction of the ultimate load bearing capacity in our case. So all these methods say that you have to include area, and then the importance increases from blue to red. By the way, that the value of the blues means the blue clusters are together means it's less important for those particular data in the database, and then it shifts towards red means that it's more important. It gets more important for those particular data again towards when you use that input feature. Let's just say cross-section area or length in this case, for example, then that data point in the database will be more important with that feature, input feature, in getting the most accurate load bearing capacity value. So again, this is called global interpretation. And all the models show here that the pile cross-section area has the major effect towards predicting the pile bearing capacity. Obviously, it's not the only parameter, because we say, okay, what happens when you want to use all these features together, or what I say, a statistical joint group in predicting the final output. So, for example, what you see here is coalitions. We call coalitions. These coalitions the larger the coalitions means in the bar plots here for each one with the different color here for each machine learning method, including the RF. The more that particular correlation is necessary to get the accurate output in terms of prediction. So, for example, this should be these arrows. I want to show you indicate for example, the very first one, A, means cross-section area, means that all the coalitions that include A, not just A itself, cross-section area itself, but all the coalitions that use cross-section area in the subset to make the ultimate load-bearing capacity prediction. And for example, A and L together are used. When they are used, the prediction's accuracy decreases, right? So A has to be used, no question, right, to get the most accurate prediction. A and L should be used. When you include QC and bearing, also, it means the prediction quality decreases. When you look at the bar heights, they decrease, right? But then what are you gonna do? You're not gonna use any soil parameter in the prediction, right? How are you gonna determine? How are you gonna rely on your ultimate load bearing capacity? So there has to be, maybe if cross-section area and length are needed on the pile geometry side or on the pile side, or these parameters are associated with the pile, then what parameters should you use that are associated with the soil side in making your prediction, right? Then when we have determined that, when you look, for example, these double, triple, quadruple coalitions, once they are all used, when you use, for example, the cross-section area length and QC end, you still get some amount of good prediction. In the bar plots are still have certain height, but then when you add QC average too, it means that and use all the four of them. Then the prediction quality decreases. And that decreases as a result of QC average, not QC end. Because when you look at the QC average, look at the arrow, the last arrow on the right, that's all the subsets that include QC average, the prediction quality decreases. So this shows that using cross-section area length and QC end is the optimum way to, or these are the optimum features to use in predicting the ultimate load bearing capacity. So what we did was we have redone all the analysis, all the machine learning analyses, but this time using only 3 features, not 4. So we left the QC average off. So we have used area, length, and QC end together in this same database, and retrained and retested all the machine learning boosting methods. And what we have come up with is that the results get better. The predictions get better for about 5 to 7%, as you can see here in the R-square values, right? So, and on the right side, the ones with 4 input features give you as good results. And
Can Hocam, I don't want to interrupt you, but we are very over time. So
I know, I'm
can you
finished.
just wrap it up? Okay,
yes, this is the conclusion, as you can see. I'm sorry. Yeah, I'm
Okay.
finished. Right. All right, good. Okay. So in conclusion, the boosting type machine learning methods work well, okay, in estimating load carrying capacity of closed-ended piles. And then Shapley is also quite applicable to determine what input features are necessary to make the highest quality possible predictions, especially in our case for the load-bearing capacity of piles. And then we have determined that 2 geometric pile parameters, length and cross-section area, and 1 single soil parameter, in this case the tip bearing and bearing of CPT associated with the pile tip, right, are sufficient to come up with the most accurate prediction. And so that's all I can say. Thank you very much for TÜBİTAK for supporting our work in this 1001 project. And thank you for listening to me.
Okay, thank you for your presentation. This was the last presentation of our session. Thank you, all of you, for making your presentations. And I want to especially thank to our director, Göksel Şimşek. He organized it very well. So, Cavit Hocam, I think you want to say something too. And I'm stopping my words here. Thank you for this conference.
I would like to thank you for your wonderful session, Chairperson. You've been very patient with your things. I think some of them should have obeyed better because the time limit is important. Therefore, we will close the day and we will be opening again for the second day tomorrow morning at 9 o'clock for 3 distinguished scientist keynotes, and then we'll go for the afternoon as well. I think it's been a tremendous day, very successful, better than we thought. Most of the speakers speak. Our session chairs are perfect. Thank you for the chairpersons and the presenters as well. And the presenters were very good papers, very good papers.
It is why I didn't want to stop them, Cavit Hocam. So,
yes, I know. You couldn't resist the temptation.
Yeah.
Exactly. I mean, I know because, for example, Martin's, actually Martin, of course, is the son of Ivan Vanecek. And Ivan, he was here in our first conference with his wife. And then he came every conference here. And I met him in Sydney, and he was going to come here as well, but he couldn't connect. So tomorrow he's going to chair Professor Munir's session. He will be here with us for the 5th time in this conference. Our friends are supporting the conference because we are doing a good job. We are doing a good job because our session chairs persons are very good and the presenters are very good. Thank you all. And can we take a picture, although we couldn't take it initially? In the opening ceremony, we took the picture with the president of the Turkish Republic of Northern Cyprus. All of them were there, but unfortunately now it's late, 7:36. Our Göksel, can you take a picture of us? Is it possible? Göksel.
I took it.
I'm catching a bus, never feeling it's really